Okay, everyone, welcome to Chapter 10. I really like finishing the course with Chapter 10 and not Chapter 11. So Chapter 10, I'll explain why. Chapter 10, it's about parametric equations and polar coordinates. So we're going to just learn what parametric equations are. And you see that is 10.1. And we're going to learn what polar coordinates are. And we're going to, after we just learn what these things are, then we're going to see how calculus applies to them. So this chapter really feels like we're going back even into like Calc 1, but we're learning just derivatives, integrals, and as they apply to these different style equations and this new coordinate system. I think it really ends the course, in a, I wouldn't say easier is not the right word, but it's just got that kind of refreshing sort of a feel to it, which is helpful when you come to the last month of a semester. Really prefer that than ending the course on Chapter 11 and particularly ending it with Taylor series and and that sort of stuff. Okay, so here we go. Chapter 10, parametric and polar, and we begin with parametric equations. No calculus here. We're just going to get used to what these equations are. Okay, so what's going on in 10.1? I'd like to introduce it with this example, this diagram. Okay, so imagine, I've got my XY plane, and I'm going to think, the best thing I could come up with. And this is not very good. I'm sure there's much more interesting things, but I've got like a little tank sitting here at the origin, and it's pointing its cannon kind of up into the air, and it's going to fire a projectile, and that projectile is going to follow this parabolic path, right, until it strikes there on the x-axis. And so, it might be helpful to know what the equation of that path of that projectile is going to be, so we know where it's going to land, right? So let's say, I'm keeping it simple here, y equals negative x squared plus 6x. That would give us that parabola coming out of the origin, and again, an x-intercept at 6. Okay, so here's the thing. So when it comes to maybe this projectile going through the air, we've described it in terms of two variables, x and y. We know its horizontal location and its vertical location. But there is another variable happening sort of behind the scenes that is not considered with the way we've written the equation x and y. What is that third variable? We know the flight path, we know the position, but when was the projectile at any given coordinate? So we're neglecting time when we're thinking just position. Well, if it's 2 units horizontally, then it's so many units vertically. Okay, that's great, but there's some time that's passing, right? How is time involved? How long might it take to get to that spot horizontally? How much time has passed before it gets to that spot vertically? That sort of thing. So I'm just gonna kind of start us off, just intro example, right? So I'm going to say, let's say the projectile travels at 4 units horizontally each second. Let's say we know that. Every second it moves 4 units in the horizontal direction. Okay, then what can we say? Well, we could say that x equals 4t. Okay, so we're thinking of x in terms of this new variable time. Every second that passes, it moves 4 units horizontally. Well, then it's only going to take 1.5 seconds, right, until it strikes, if we just think horizontally. But, of course, we might want to know where it's located vertically after any given time period. So then we can combine our x equals 4t with the original equation, just the substitution. Put your 4t in for the x's, and clean it up a little bit, and there it is. Y will equal negative 16t squared plus 24t. if we do that substitution for the x's. So for any given amount of time now, we can know where it is vertically, also horizontally and vertically. So you notice we've actually kind of thought of this as two separate functions. X and y are still connected to each other, but they're now connected through this third variable, time. Okay. I think that introduces this well. Let me just kind of show you what these will look like in general. Parametric equations in general, you'll have a function with x equals some function of t, and y equals some other function of t. We'll say x equals f of t, y equals g of t, just to give them names here. Where does the name parametric come from? We call the t the parameter. And so hence parametric equations. There's always this pair, an x and a y. Sometimes we will use another variable, not t. Occasionally we'll think of an angle, theta. We'll see that a little bit later in this section also. Okay, but usually it's t. That's the go-to because it represents time. Finally, you might think about the graph of a parametric equation. We call it the parametric curve, or sometimes you hear the expression plane curve, and we actually give it a name, C. So usually we don't give graphs a label, but for parametric equations we do. The parametric curve is denoted capital C. What's the difference? It's the same graph as it would have been just with x and y, but now, because we can think of time passing, we're going to put arrows indicating the flow of time, indicating direction, which is exactly what we had done back here, right? There are these arrows indicating time passing. Okay. Well, hey, let's get into, I think we can get our first example here. Sketch the curve, indicate the orientation. By orientation, we mean the arrows indicating the flow of t, time. And finally, we're going to write the parametric equations into, write the Cartesian equation. The Cartesian equation is the traditional form that we're used to with just x and y. Okay. So here we go. We're given these parametric equations. X equals t to the third, y equals 1/2 t squared. We are going to begin with sketching that curve. And right now I'm actually trying to just grab another piece of paper so I don't show you all of my work at once. How can we sketch this curve? Okay, here's what we're going to do. We're going to make a table. All right. And I've got it all filled in already, so I don't want to show you everything. I'm going to have a t row, an x, and a y. Okay, so I'll show you the x and the y in a moment. But I start off just making this big table, t, x, and y, and then I make these rows. Okay. I decided for this problem we just need enough information to sketch this curve. There's no rules here, just guidelines. I usually would say 5 points, 5 values of t is going to be good. There's going to be other times where you might want to include more if you're not quite sure how the curve plays out, how the dots connect. I'd say a minimum of 5 is a good idea. So I chose, you want some negatives, some positives, 0 is a good idea. I chose t to be -2, -1, 0, 1, and 2. So I'm going to take those values of t one at a time, plug them in for x, get the x coordinate, plug it in for y, get the y coordinate, and we'll do that for all of them. Okay, I'm just going to show you what I've got here. Feel free to pause the video and just make sense of this. So I started with -2, put it in for x. Okay, that's -8. Took -2, put it in for y. That's +2. And I went through each value of t, getting the x and the y values for all of them. Okay. Why did I pick just these? Hey, I could have gone -3 and +3. I'd like to stick with the whole numbers, and some negatives, some positives. Zero is a good idea. Okay. So then I'm just going to draw an XY plane like normal, and I'm going to graph each of these 5 points. Negative 8, 2, negative 1, 1/2, 0, 0, 1, 1/2, 8, 2. Just those ordered pairs as I normally would graph. Okay. Now when I show you this, it's actually the full graph with the arrows and everything. I think that will be okay. We'll just point to what's relevant. So I would start by graphing, negative 8, 2, and then negative 1, 1/2, 0, 0, 1, 1/2, and finally 8, 2. And you see I've kind of labeled, just the pieces that I need. I don't have to be incredibly detailed, right? Sketch, we want to be detailed enough, but it doesn't have to be to scale. Okay, once I have those 5 points plotted, I think that's plenty enough information for me to get a good picture of this graph just with those points. So I can say, okay, the curve, it's coming down, it passes through this point, it goes through 0, 0, and then it almost like bounces and goes up that way. And finally, I can tell how the arrows are working because I'm thinking time is passing. So the lesser values of t to the greater values, right? Kind of like working this direction. So the first value there was here, and then that was negative 2, negative 1, 0, 1, and 2. Those values of t are passing this way. And it almost looks like, maybe somebody threw, a ball, and it came and bounced against the pavement and then continued bouncing along its path. Something like that. Okay, so we have the curve. We indicated the orientation with arrows. Now finally we need to write the Cartesian equation. What is the more familiar equation with just x and y for that same graph? Okay, well, turns out there are a couple different methods for some examples we'll see, but this one, where it's just polynomials for our t's, pretty straightforward. Actually very much like that example with the tank we saw a moment ago. So how are we going to start this thing? Oh, I have this note here. If you'd like to confirm that this really is the parametric curve, and you notice I even labeled it C right there, you can do that in Desmos very easily if you graph it like it's an ordered pair, but instead of numbers you put in your x function and your y function just like that. It will recognize, if you use t, it will recognize that you're talking about a parametric curve, and it will give you that graph. You have to play with the values of t that it will input, but it's all right there, very user friendly. Okay, let's get that Cartesian equation. How's that going to happen? Well, I'm kind of scrolling down here. All right, I don't want to give everything away. Oh man. Okay, so we're going to begin with, all of a sudden my writing got smaller. It almost appears. So I'm going to start with x equals t to the third. Hey, would you agree that if we solve for t equals x to the 1/3? Okay, yeah, I think we would agree with that. So then I'm going to take x to the 1/3 and I'm going to put it in for the t in the y, and that's it right there. So I take almost, it's similar to the example with the tank, not identical. So I take the x, I plug it in for t there, simplify, boom. It's like the reverse of that previous example. There's the Cartesian equation, the way we're used to seeing it. Y equals 1/2 x to the 2/3. Okay, I've got part B coming up next. I think we'll save that for the next video.